Okay, hello friends, Mr. Burrell here. We're in the unit about exponentials and logarithms, and we've talked a little bit about some basic exponential properties, some properties associated with exponential functions. Today we're going to talk about graphing exponential functions, how we graph exponential functions, some of the special properties of exponential graphs. So that's what we're going to start talking about today. By the end of class today, I would hope that these are some of the things that you're able to do at the end of this lesson, I should probably say, since you're not in class. At the end of this video, I would want you to be able to identify if an exponential function is a growth or decay function. I want you to be able to identify a horizontal asymptote of an exponential function. I'd want you to be able to identify the domain and range of an exponential function and graph exponential functions by plotting points and with a calculator. So those are some of the things I hope that you're able to get by the end of this video. Okay, so I have three tables here. I have f of x is equal to 1/2 to the x power, f of x is equal to 2 to the x power, and f of x is equal to 10 to the x power. Each of these are exponential functions. Exponential functions are characterized by having a variable, or in this case an x, in the exponent. So that's what makes an exponential function exponential. That's what gives it the special properties that we talk about, is when the x is in the exponent. So we're filling out just a table of values, x and y values. So if I give you these x values, and I've already filled it in for you, these are the corresponding y values for each of these graphs. I'll fill in these with decimals so you can have an idea of what's going on here. So right off the bat, I am able to plot some points on a graph representing this exponential function using the equation that's given to me. So you notice here I have the point -3, 8, -2, 4, -1, 2, etc., 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 0.125, 0.25, 0.5, etc., etc., etc. So the next slide, I'm going to show you what these graphs are going to look like. So if I were to transfer the information from that last, let me move this camera out of the way, from that last slide onto here, I have f of x equals 1/2 to the x power, f of x equals 2 to the x power, and f of x equals 10 to the x power. So you noticed on that previous slide I had the point -3, 8, -2, 4, -1, 2, I think it was like 0, 1/2, etc., etc., etc. So it kind of starts off really high and ends off really low. This graph, I had 0, 1, 1, 2, 2, 4, and then I had -1, 1/2, and 1/4, and 1/8, etc. So this graph kind of starts really small on the left and then gets really big as I move farther to the right. Same here with f of x equals 10 to the x. It starts really small over here, it gets really big over here, and in fact it gets big really, really quickly, because right here I start off at point 1, I have a y value of 10, so 1, 10, whereas over here I only had 1, 2. So this graph over here grows a lot faster. So we're going to talk about some very specific characteristics of all these graphs. You notice between these graphs there's a lot of things that are similar, the same. There's a lot of things that are different, and we're going to characterize those graphs here in just a minute. Oh, whoops, let me go back. Okay, so if I were to just draw like a rough sketch, here was y equals 1/2 to the x power, here was y equals 2 to the x power, and this maybe would be, oh, that's a terrible graph, this would be y equals 10 to the x power. So let's identify some of the things we see in common between these different graphs. So first of all, we're going to characterize these graphs by either a growth function or a decay function. Growth meaning as x gets bigger, y gets bigger. Decay meaning as x gets bigger, y gets smaller. So you notice here, as I go from left to right, as x gets bigger, this graph falls down. It gets smaller. Y approaches 0. So this we're going to call a decay function. It's constantly decreasing or decaying. Conversely, each of these functions, as I go from left to right, they're increasing, they're getting bigger. So I'm going to call these two right here, growth functions. So first characteristic of these different graphs, either a growth or decay function. You'll notice if I have a fraction right here between 0 and 1, that's going to give me a decay function. If I have a whole number here, that's going to give me a growth function. Next, we want to find out what the y-intercept is. If you notice on these graphs back here, well, we won't go back for now. The y-intercept is where I touch the y-axis. And when I touch the y-axis is when x is equal to 0. Right here is where x is equal to 0. So if I were to put 0 into each one of these equations, 1/2 to the 0 power, 2 to the 0 power, 10 to the 0 power, anything to the 0 power is 1. So when x is 0, y is always 1. So on all of these exponential graphs, the y-intercept is at 0, 1. It crosses the y-axis at 1. Every single time in this form of an exponential function. I think that's pretty cool. That's pretty handy. So the domain, if you've forgotten what the domain means, domain is all of the possible x values that a function can take on. Or in other words, if I'm walking across the x-axis, how far am I going to be able to go in both directions and still have a graph happening? So here, if you notice, if I were to keep drawing, that's a terrible picture, but if I were to keep drawing this going left and left and left and left and left and left, it's never going to stop. It's going to keep going. So I'm going to be able to go all the way to negative infinity. Conversely, if I follow this side of the graph all the way going this direction, I'm going to be able to go to positive infinity. Any real number I can put in for x here. Any real number is a possibility. Negative numbers, positive numbers, really big numbers, really small numbers, all of those are a possibility. So in every single one of these exponential functions, the domain is from negative infinity to positive infinity. So the range, we're talking about all the possible y values that I can get out. So notice here on all of these functions, on all of these graphs, I only have graph above the x-axis. It never goes down here. It gets really close to the x-axis, but it never goes below into my negative y values. So the range is going to be all the positive real numbers, or from 0 to positive infinity. So the range of every single one of these functions right now is from 0 up to positive infinity. And we're going to talk about in just a second what I call this situation where the graph gets really close to the x-axis but never touches. But those are some of the common characteristics of these different graphs. The range is always the same, the domain is always the same, the y-intercept is always the same, and then you can determine from the function if it is a growth or decay function. Okay, so next question I want to ask is, what is an asymptote? Some of you have heard this term before. This is kind of a funny Gandalf meme. But an asymptote, oh wait, let me go back. An asymptote is a line that a graph gets really close to but never actually touches. So you see on this graph with Gandalf, this line right here would be a asymptote because these two graphs get really close to it but never touch it. In these functions that we have, you'll notice that the x-axis, each of these graphs get really close to touching, but they never actually will. So in each of these graphs, the horizontal, or flat, this line right here, the horizontal asymptote in each of these graphs is y equals 0. So when y equals 0, which is right here, this line is the horizontal asymptote, a line that the graph will never touch. So you noticed before we had the range outlined on each of these functions as going from 0 to infinity. I kind of cut that off. But since the range is from 0 to infinity, that helps me to determine that the horizontal asymptote is going to be at 0. I can't go any lower than that, so the asymptote is going to be at y equals 0. Okay. So to kind of give us an idea of how these graphs might change. All of my exponential functions are going to look something like this. A to the x minus h plus k power. We've already determined that this a is going to determine if it's a growth or decay function. And a little bit today and a little bit over the next couple days, we're going to talk about how this h and k affect these graphs. Specifically, today we're going to focus on how those will affect the horizontal asymptotes. So, I'm going to crawl in here and come to Desmos real quick. And we're going to experiment with what happens when I change those different letters. So we're going to go to graphing exponentials here. Okay, so for example, if you have guided notes, you'll have these. But I have this function, just plain Jane 2 to the x power, y equals 2 to the x. It looks like this. Very similar to ones that we've already graphed. It passes through the point 0, 1, and it has a horizontal asymptote at y equals 0. So how is this graph going to change if I type in 2 to the x minus 1? So if I change the k value in that function, how is that going to affect this graph? Think for a second what you think is going to happen. But that minus 1, that k value makes it drop down 1 unit. So instead of it crossing the y-axis at 0, 1, that point's going to drop down 1 and be at 0, 0. And notice now that the horizontal asymptote is at y equals negative 1. So instead of y equals 0 being the horizontal asymptote, y equals negative 1 is the horizontal asymptote. And now the range goes from negative 1 to positive infinity. So that negative 1 right there, that k value, is going to drop my graph down 1 unit. Here's y equals 3 to the x. Again, crosses the y-axis at 0, 1, has a horizontal asymptote at y equals 0. How do we think 3 to the x plus 4 is going to affect this graph? It's going to make it go up 4 units. Now the horizontal asymptote is at y equals 4, and it crosses this point at 0, 5. 4 units up from 0, 1 that we were just at. And now the range is anything greater than 4. So how is this going to change it? How is this going to affect the graph right here if I add an x minus 1 up here in the parentheses, in the exponent? Let's check. Is it going to move it to the left? Is it going to move it to the right? Is it going to move it up? Is it going to move it down? Well, there you go. It ended up moving it to the right. So notice here, this 4 out here, the k value moved it up 4 units, and then that negative 1 in the parentheses in the exponent moved it right 1 unit. So this point right here should be about 1, 5. So going from 0, 1, we went up 4 units to 0, 5, and then right 1 unit to 1, 5. And that is the transformation, and we're going to talk more about these in a couple days. But the big one that I want you to understand here is that this 4 right here gives me the new horizontal asymptote at y equals 4. Because notice if I have a function like this is an exponential decay function. The x plus 2 here will affect the graph moving from left to right, but it will not affect the up and down, so it will not affect the horizontal asymptote. Okay, we won't experiment too much with that right now. But that is basically what I want you to understand. This k right here is going to affect the horizontal asymptote. And we'll talk more about and focus more on both of these changes in the next couple days. But for right now, I want you to focus on the fact that this k value out here is going to affect the horizontal asymptote of that graph. Okay, so I want you to go ahead and read through those. Those are the things that I hope that you're able to understand at the end of this video, at the end of this lesson. I hope that was helpful, and I hope that you enjoyed that as much as I did.